Airy's equation is y double prime minus xy equals 0. This can be used to model an undamped vibrating spring with spring constant x. The solution to this differential equation will tell us the behavior of a mass spring system as the spring ages. Starting off, assume a solution y equals f of x has a series that can be written in the form y equals the sum from n equals 0 to infinity of an x to the n. Where the coefficients are undetermined, our job will be to find the coefficients.
Our first task is to find a series for y double prime. So as Joe mentioned, we know that y double prime minus xy equals 0, and we know the series for y is a sub n x to the nth. So to find the series for y double prime, we're going to have to take the second derivative of the series for y. Taking the first derivative, we take that n and we move it out front. Then we have to subtract n from that exponent, as it's just x to the nth is the function we're looking at. So to take the second derivative, we have to take that n minus 1 and move that out front as well. And then we have to subtract another one from the power. That gives us the series a sub n times n minus 1 times x to the n minus 2. Now you may also notice that each time we take a derivative, we move the index up by 1. That is because we want this first term to always be 0. So the first one, x to the 0, is just x to the 0. For the second one, x to the 1 minus 1 would give us 0, and for the final one, x to the 2 minus 2 would give us 0.
So now our job is to combine these two equations that we have. So we know that y double prime is equal to this beautiful equation given by Mark. Now we need to get y into a more favorable equation, so we're going to distribute the x. Since they are like terms, we can combine exponents. This will be x to the 1. So if we combine those, that'll be x to the n plus 1. And then we just plug it into, y prime minus xy equals 0. And we get this wonderful equation down here, which we can go and do more math with.
Now, we want to combine the series on the left in equation 2 with the equation on the right of equation 2. But we have different powers of x. So we want to change our index to get even powers of x, starting with our sum from n equals 2 to infinity. So in order to change this index, we want our first term to be the same. So for this sum at n equals 2, our first term is 2a2. This being x to the 0, a2 multiplied by 2. In order to change this index, we're going to want to add 2 to every n in order to keep our n's at the same value each time. So adding 2 to each term gives us n plus 1 times n plus 2 times an plus 2 x to the n. And if we go ahead and double check our n equals 0 term, we get 2a2, which is equal to our n equals 2 term. So therefore, the sum from n equals 2 to infinity of n minus 1 times n times an times x to the n minus 2 equals the sum from n equals 0, n plus 1 times n plus 2, an plus 2 x to the n.
So given what Wyatt showed us, the sum for x times y is an times x to the n plus 1. Now going off what Joe did, we don't want that x to the n plus 1. We got to get rid of that. So we need to shift the index by 1 to get the power x to the n. So to do that, we need to subtract 1 from each term with an n in it. So a to the n would go to a to the n minus 1, and x to the n plus 1 would go to x to the n. And since we're shifting the n value, we're going to have to shift the index up by 1. And that shows us that the sum of a to the n x to the n plus 1, starting at n equals 0, is the same as the sum a to n minus 1 x to the n at n equals 1.
Alright, now we can substitute 4 into equation 2 to obtain this beauty right here. So let's start with equation 2, which is given by this. All we did in equations 3 and 4 were switch the indexes so that we have even powers of x, that being x to the n. So for this series, all we did was switch the index down to 0, which is given by this. And for this series, we switch the index up to 1, which gives us this. Now what we want to do is we want to combine both these series and extract the x to the n. And in order to do that, we can't change the index again, because that'll give us, say if we were to change this index to n equals 1, this would give us x to the n minus 1. We don't want that. We want to be able to extract these x's to the n's. And in order to do that, we're going to extract the n equals 0 term from this series, and that'll give us a new series starting at n equals 1. And that is given down right here from C. We know that the n equals 0 term is 2a2, which is being added to this series starting at n equals 1 minus sum n equals 1 to infinity of a n minus 1 x to the n. Now we can combine these and extract our x to the n, which gives us this.
Alright, so using the equation that Joe so graciously gave us, we are able to add this left-hand side of the equation over to the other side. That gives us 2a2 plus that sum equals to that sum. Now both of these sums are constants times x to the n. So these constants would have to be the same to be equal. Thus, from that we can infer that a2 would be equal to 0. Going off the basis that we know a2 is equal to 0, we are able to try and find a term that would be equal to a2. So if we plug in n equals 0, n equals 1 to this equation, or n equals 2, that doesn't really help us, because that gives us negative 1, a to the 0, and a to the 1, which we aren't entirely sure what those equal yet. So the first term we're going to have to look at is n equals 3. Plugging in n equals 3 gives us some positive constant times a5 is equal to a2. Thus, because a2 is equal to 0, we can infer that a5 is equal to 0. So, going on from that, we have to get some term equal to a5. N equals 6 gives us that. So, plugging in n equals 6, that gives us some positive constant times a to the 8, because 6 plus 2 equals a to the 5th, because 6 minus 1 is a to the 5th. Thus, we can tell that also equals 0. Again, we can do the same for n equals 9. And that gives us that for every value, a to the 3n plus 2 would equal to 0.
Now moving on to a to the 3n values, we have this beautiful sequence. If we were to plug these in, and doing so, to the previous equation that we've had worked out, we would get 2 times 3 times a3 minus a0 equals to 0. We can arrange this, and we get this wonderful fraction, a0 over 2 times 3 is equal to a3. Moving on to n equals 4, if we plug that in, we would get 5 times 6 times a6 minus a3 is equal to 0. And then we can rearrange to get a6, which is a3 over 5 times 6. And we know what a3 is due to this previous one that we did up here. So if we plug that in, we get this funny a0 over 2 times 3 times 5 times 6. And this pattern repeats if we go on to n7. We notice that we get a0, 2 times 3 times 5 times 6 times 8 times 9. So we can conclude that a3n is equal to a0 over 3n minus 1 times 3n.
Next, we want to prove that a3n plus 1 is equal to this fraction a1 over 3 times 4 times 6, so on and so forth, times 3n times 3n plus 1. First, we're going to want to look at the sequence 3n plus 1 to find some values of our terms of a that we're going to want to be looking at here. In order to get two a terms with these values, we're going to want to look at n equals 2. This will give us a4 minus a1. We can rearrange this to a4 equals 1 over 3 times 4 times a1. Go on to n equals 5. We have more terms that lie within this sequence. We have 6 times 7 times a7 minus a4 equals 0. We can rearrange this again, having a7 equals 1 over 6 times 7 times a4. From here, we can go back. We know what a4 is. Substitute that in, and we get 1 over 3 times 4 times 6 times 7 multiplied by a1. This trend will continue, so on and so forth, to 1 over 3 times 4 times 6 times 7, so on and so forth, times 3n plus 1 multiplied by a1.
Alrighty, so now to kind of bring this all together and do a little recap. We started with Airy's equation up here, and we had the assumption that y is a function that is equal to the sum of a n to the x to the nth power. And then we took the second order derivative of this in order to plug them back into the original equation to get this wonderful summation here. And then we needed to change the indices of these in order to combine them with the x's having the same ordered power. And then we finally combined those all together in part E, and then in part F we needed to find all a values for this, so we know that all a3n to the 3n plus 2 values are all equal to 0. We know that all a3n values are equal to a0 over 3n minus 1 times 3n, and then we know that all a3n plus 1 values are a1 over 3n times 3n plus 1. And then going back to our original y summation here, we can plug that all in. However, we need our indice is 0, so we need to extract our first values out within this to get our final equation for y.
All right.